Yeah, so now we are dealing with what you call the systematic the systematic mineralogy. And then we're gonna be looking at the hydroxides and the halides. So basically the systematic mineralogy, it involves the mineral classification and the description of mineral physical properties. So, the minerals are classified based on their chemical composition and also based on their internal structure. So, what we like to say is the internal appearance or the internal structure, it reflects the external appearance of a mineral. So, what we see externally represent the internal structure, because the atomic arrangement of the atomic arrangement within the mineral or the crystal lattice, it would reflect the external appearance of that particular mineral. It means the atomic arrangement of that particular mineral, it will determine the physical properties of a mineral. That is to say, how the mineral will appear. That's why now the minerals belonging to the certain an ion or an ionic group, they usually occur together, or they belong to the same, or they occur together in the same geological environment. So today, we last week we dealt with oxides. We are done with oxides, and then now we are into the hydroxides and the halides. So we are done with the oxides. So the hydroxides, they have got the OH or the hydroxyl group, and then halides, they've got the halogens. So there's halogens, that is to say everything from group 7, chlorine, fluorine, bromine, and iodine, right? So the halides, they've got these they've got the halide group, meaning they have everything from, or they contain the halogens. And then the hydroxides, they've got the hydroxyl group. So if you can check over here, this is the for example, Brucite, this is the hydroxide, and this is the halide, right? This is the halide. So hydroxides, they contain hydroxyl group OH, bonding to a metal cation or polyatomic ion. But on the other hand, halides, they are formed by halogen elements. Everything that belongs to group number 7. Okay. Now, these halogens, they're going to bond with other metals. For example, if you take halogen chlorine and then you bond it with element sodium, you're going to form a sodium chloride, okay, which is a halide. Or you can have potassium and chlorine, and you'll form what you call sylvite, potassium chloride. So okay, now see that these halides, they are formed when you take element from halogens, and then you bond it with another element, and then you're gonna form, what am I doing? You're gonna form what you call a halide. So each type of a compound has distinct properties and systematic ways of being described based on their chemical composition. Okay, so everything is remember we said the minerals, they're classified based on their composition and also based on their internal structure. So the halides are compounds formed by halogen elements like fluorine, chlorine, bromine, iodine, or astatine. Okay, and then you bond that with another element. They can be ionic or covalent, meaning they can be a transfer of electrons or they can be sharing of electrons, depending on the electronegativity of elements which are involved. And then halides, they're classified as fluorides, chlorides, bromides, iodides. But the most common ones, which we're gonna talk about more today, will be fluorides and basically will be fluorides, okay, and the chlorides, okay, will be fluorides and the chlorides. Halides may play important roles in various chemical reactions, and their properties can vary widely depending on the halogen and the element they are bonding with. Obviously, if you are sodium chloride, it will be different to a sylvite or the bromine one. Okay, because of these things, they are varying. So examples of halides will be sodium chloride. This is the table salt we are most familiar with. Hydrogen fluoride, and then sylvite. So can now see that we everything every halide we have the halogen group: chlorine, fluorine, chlorine, fluorine, bromine. Bromine. Okay, so and then bonding to at least one element. But all of these halides, they're generally softer compared to oxides and hydroxides, and then typically they occur in evaporates, meaning they form when something it evaporates, and then they would leave, especially in the arid regions, when in semi-arid regions or arid regions, when we've got saline water, okay, especially also in lacustrine or in the shallow seas, when you evaporate, when evaporation happens, the remaining, or when they occur over millions and millions of years, they will form these halides. Okay.
Yeah.
So this is, for example, this is what you call a sylvite, meaning potassium chloride. This is what you call a halide. Okay, and then this is what you call the is this one. Okay, calcium bromide. Calcium bromide. Okay, is this one. So all of these halides, they are composed of, or they consist of metal cations: sodium, potassium, and calcium. Okay, and then all of them, they have got the high solubility in water. That's why salt can dissolve in water, because of the group of halides. All of them, they are relatively high, they have got high solubility in water. Okay, and then they have got good cleavage and transparency, meaning if you can take the halide, you can be able to see through. They are transparent. Okay, then fluoride, fluoride, okay, it has a perfect octahedral cleavage, and then but the most distinctive feature is it glows under what you call the ultraviolet light. So fluoride, it has got what you call the fluorescence. It means if you expose it to ultraviolet light, it will glow. Okay, I'll show you different colors. Okay, and it has got a wide range of colors. It has got rainbow colors. Okay, so that's why we say fluorite occurs in a variety of vibrant colors, including purple, green, blue, yellow, and even colorless. This wide color range is due to different trace elements and structural defects within the mineral. Okay, and then one of the fluorite's most famous properties is its ability to fluorescence under the ultraviolet light, often glowing in shades of blue, green, purple, or other colors depending on the impurities. Okay, so it means if you want to know that I'm dealing with a fluoride, the first thing is it must have under UV, it must glow. Okay, so for example, it has got these rainbow colors. That is the first thing, and then this is fluoride under UV. Okay, remember different colors is due to impurities, but under UV, you will see this glow. Okay, you will see this glow. The most common one is this bluish one. Okay, so if under the UV it shows these colors, then I know that I'm dealing with the fluoride. Okay, so fluoride has got many colors due to the impurities. It has got these many colors due to the impurities. Okay, but the most important part is this fluorescence and the perfect octahedral cleavage. Okay, it means it has got the perfect cleavage in 4 directions, forming octahedral fragments. This makes it easy to distinguish it from other minerals. Okay, So that's why we're saying it has got a perfect cleavage. It has octahedral. It has got the octahedral shape. And on the other hand, we also have got what you call the hydroxides. Hydroxides, they are containing the hydroxyl group OH. And then this OH, you are bonding it to a metal a cation or a positively charged polyatomic ion. They are often considered basic compounds and can react with acid to form water and salt. Okay. Many hydroxides are insoluble in water and form precipitates when mixed with aqueous solutions of certain ions. Hydroxides are generally low in density and they are relatively softer. It means they are not they are easy to be scratched with a coin with the coin, okay, because they are relatively softer. This is the general properties of all the hydroxides. The bond between the metal cation and hydroxide ion is in hydroxides is typically not as strong as the bonds in other bases like oxides or alkyl oxides. Meaning, because of this bond strength that is weak, it makes these hydroxides to be relatively softer, and also because of the presence of the OH, this hydroxyl group, it makes these things to be relatively softer. These weaker bonds, it makes it easier for the hydroxide ion to dissociate, resulting in a less effective base. They can dissociate or break down, meaning that hydroxides are relatively weaker than oxides. This is because of the presence of OH. Like I said, this OH, it makes them to become weaker. Okay, the presence of this OH, which causes the bond strength in the structure to be weaker. Okay, so we're gonna be talking about these types or these the most common hydroxides that for example limonite, goethite, gibbsite, and other ones. But now, the most important processes which form these hydroxides is weathering and what you call hydration. So, hydration is when you are incorporating OH in, or you're incorporating water into the crystal structure of these minerals. And then weathering is the process by which the rocks and minerals are broken down and they are altered by exposure to atmospheric agents such as water, oxygen, and carbon dioxide. So when you expose the minerals to these water, oxygen, and carbon dioxide, these minerals, they tend to break down. Okay, then we've got different types of weathering. We've got chemical weathering, we've got physical weathering, and biological. But most important part is this weathering. It breaks down the minerals. So when certain minerals, for example, um, when certain minerals containing metal cations are exposed to water and atmospheric carbon dioxide, they undergo chemical reactions that result in the formation of hydroxides. For example, feldspar minerals, all these feldspar minerals, such as plagioclase and orthoclase, they can weather to form clay minerals and release metal cation, calcium, potassium, and sodium. Okay, and then also with hydroxide ions. So can you see that hydroxides, they can also form through weathering. When we are weathering these plagioclases, they will give you these cation, these metals or these cations, and then along with the hydroxide ions. Carbonate minerals, on the other hand, they can weather to form calcium hydroxide along with dissolved carbon dioxide and bicarbonate ions. These reactions involve the dissociation of minerals in water, followed by chemical rearrangement that lead to the release of hydroxide ions. And we have also what you call the hydration, wherein you're incorporating water into the structure of that particular compound. Okay. So, for example, certain metal oxides can react with water to form metal hydroxides. This process involves the incorporation of water molecules into the crystal lattice of the oxide. Then that, when it happens, it will result in the formation of hydroxide ions. For example, when we have got iron oxide minerals such as hematite, when we were talking about oxides a few days back, we talked about the simple oxides like hematite. So hematite, when it undergoes hydration, when you incorporate the water into the crystal structure of the hematite, you can form iron hydroxide, like what you call the goethite, which is why goethite, it is iron hydroxide. Are we together?
Yeah.
Okay. Now, I want you now to be able to physically identify these common hydroxides: goethite, limonite, brucite, and gibbsite. These are the most common hydroxides. Goethite. This is the iron hydroxide. How does it form? How does it form? It forms when hematite undergoes hydration. Okay. Sorry. The color is usually brown, yellow brown, or reddish brown, with variations depending on the impurities. Streak, it produces a yellow brownish to orange or brown streak. Okay. And then hardness is usually 5 to 5.5, and so it is relatively softer. Okay, luster, it will ranges from earthy in massive forms, and then to silky or metallic in fibrous. Okay, so you'll see that you can have the goethite, which is earthy, and is dull and dull and massive, and then you can have the other one, which is metallic, and then it will be a bit silky. So this one, it's metallic, so it has got this fibrous texture. Okay, it's still a goethite. So we have got the other one, which is metallic. So how would you know it? How will you be able to identify it? Because of this fibrous texture. Okay, and then this one is the one which is earthy. It means if you were to have it, you will see the dirt inside your hand, or wherever you put it, you will see the dirt. It means it's a goethite. That is also the another distinctive feature of this goethite. It's earthy. Are we together?
Yeah.
Okay, limonite. The distinctive feature is this streak. Okay, is this streak. The streak, which is yellowish brown, that is the distinctive feature. It will help you differentiate it from hematite. So it will have the yellowish brown, and then the luster, it will be dull to earthy. Can now see is dull to earthy. Earthy, like I said, wherever you put it, it will leave the dirt. Okay, and then it will be dull. And then color, it will be yellow, brown to dark brown. For example, here you are having this dark brown, and then here you are having this yellow to brownish in color. And that is the limonite. But the distinctive feature, it will be this streak, the yellowish brown, and also this color, the yellowish brown. And then we also have got a brucite. The brucite, the distinctive feature is this perfect basal cleavage, which will break into thin, flexible sheets like the one of micas. Luster, it is pale to vitreous. Okay, and it has got low hardness. Okay, it has got low hardness. So color, it's white, pale green, blue, gray, and sometimes it can be yellowish with a hardness with approximately 2.5 to 3. Okay, so this is what you call the basal cleavage. This is what we call the basal cleavage. Okay, like the one of the micas. Okay, they are right on top of the other, so that is the distinctive feature of this brucite, the basal cleavage. That will help you to know that I'm dealing with the brucite. But we've got the other ones which are colorless. I've got this one which is pure, it means without impurities, and this one's shady yellowish. This color is like the one here, the aquamarine, that type of a beryl. Then it's due to the impurities. But how do you identify brucite? This vitreous or the glassy luster, and also the basal cleavage. These are the distinctive feature of these minerals. Are we together?
Yeah.
Okay. Okay. Then we also have got what we call a gibbsite. All these things, they are hydroxide because they have got OH in their crystal structure. So the gibbsite, it is usually white, gray, or colorless, but can appear pale green or blue due to the impurities. Okay, due to the impurities, and it's relatively soft, also from 2.5 to 3.5. Okay, and then it can be scratched by a copper coin because of, remember, hydroxides, they've got weaker bonds. That's why they are not that hard, and that's why they are weak. You can also be able to scratch them. And then it has got this vitreous to pale luster, giving it somewhat shiny appearance. And then the streak, it is white. Okay, so a good way to identify gibbsite is by its low hardness and a perfect cleavage. Okay, combined with its typically white to pale color and pale luster. So if you can tell, so if you can look at these ones, you can see this pale luster. That is the distinctive feature, and also this the streak, the white streak. Okay, and it has got a perfect cleavage. So these colors are due to the impurities. Are we together? So this
Yeah.
this is the gibbsite. This is the gibbsite. Is what you call the hydroxide. Okay. Do you follow?
Yeah, I follow.
Okay. So I think this brings us to the end of the other systematic mineralogy. So we dealt with the oxides, we dealt with halides and hydroxides, we dealt with the sulfides, we dealt with the silicates. All right, we dealt with the silicates, and then next week, and then we'll start with the rocks now. Now, how will you be able to differentiate from just looking at a certain rock? How would you know that this is an igneous rock, this is a sedimentary rock, this is a metamorphic rock? How would you differentiate them? Then, if now you are able to differentiate them, how will you be able to identify all these minerals, all these sulfides, these silicates? How will you be able now to see them inside the rocks? Are we together?
Yeah.
Okay, so tomorrow I think later on we'll meet at this time, and then we'll deal with the pyrometallurgy. Is it fine?
Tomorrow.
Yeah.
Yeah.
Or should we make it